So let us define integrals now. The final thing in real analysis. We will not go in much rigorous concepts in this one, but the superficial bits.
Differentiability.
It's easy. Okay, we are coming at the end. It's easy. So in integrals, we will simply define what a Riemann integral is and what are the conditions for a function to be Riemann integrable. That's all. Maybe we'll do a bit about Riemann Stieltjes integral. Otherwise, it is not required because it is same as this one. So, if you want to define this, what do we mean by the integral of a function in some interval a to b? So, our function is defined from this interval to the whole set of real line. So, first of all, I have taken a closed interval because we can define the integral on this, then we can extend the notion. So what I do basically, I have an interval which is subset of R. First, I define a partition, the partition of this interval. Let us name that partition to be P. And what is the partition? It is a set of values x0, x1 up to xn, such that what happens that x0 is less than x1, less than x2 up to xn. Xn is exactly b and x0 is exactly a. This is what I call the partition of my interval. So this is my interval. I am defining some x0, x1 up to, let's say, xn minus 1, and this is exactly xn. This should be, I think, x0. This is x1, this is x2, and so on. This is the partition of my interval. So this is what we define the integral. We are not saying that okay, the integral is the area under the curve, but this is the rigorous definition of integral. You have a function defined on some interval. You are going to make some partition of your interval in this way. It is not necessary that distance between these and these should be same. It is not necessary. We can make it same. Then it makes our life easy. Then I define something else. One thing is that f is bounded, and we know very well what we mean by a bounded function. Then I take the value of the function between some interval xi minus 1 to xi, and in this interval I take the infimum of the value of the function and I name it mi. So I choose an interval from xi minus 1 to xi. Within this interval I find the value of my function and I take its infimum, that is mi. And then the supremum is going to be capital Mi. Then what I do, I take small mi, multiply with the length of the interval xi minus 1, and I take their sum from 1 to n. I call this the lower sum. I take capital Mi, multiply with the length of the interval. I call this upper sum when I take their sum from 1 to n. I call this the lower sum of the function defined on some partition. I call this the upper sum of a function on some partition P. Okay, so we are going to move ahead towards the definition of Riemann integral by using these elementary things. And here what we call P to be the partition. Okay, so we have a function defined on some interval. Function, interval. The first thing is what we do, the partition of this function. It means we take some values x0, x1 and xn such that this condition holds. then we call this to be the partition. Your initial value is same as A, final value is same as B, and all the values are on this what we call the increasing order. And one condition that I have imposed so far is what we call f is bounded. I am not saying f is differentiable, f is continuous, but only one condition, f is bounded. Then I choose an interval, any interval from this one, either this one or some interval in between. Let me name that interval to be, let's say, xi minus 1 to xi. That's my interval that I have chosen so far. I am finding the value of my function within this interval, but I am taking the infimum of that value, it means the smallest one. And I am calling that one small mi. Similarly, I am calling this supremum to be capital Mi. What am I doing? I am multiplying this small mi with the length of my interval. This is the length. And taking the sum over all the intervals, and I am calling this the lower sum, and I am calling similarly this one as the upper sum. And we know very well lower sum is sometimes called lower Darboux sum as well. And sometimes it is called lower Riemann sum. So these are Riemann sums, but one is lower and one is upper. What is the difference between the lower sum and upper sum? Basically what happens that within this interval, you can see these are the values of my function within this interval. What is going to be the infimum of these values? That lies here. So I am taking this value and I am simply finding out this area. This area is small mi, and I am multiplying this small mi, like I am adding all these small mi's. It means I am finding the areas corresponding to these below the graph of the function, below the graph. Similarly, what about capital Mi? The capital Mi is, you are taking the value at this point, then you are basically taking this rectangle. It means now you are extending this piece of area, and then you are taking this interval, and this is what we call the upper sum. What is the idea? I want to find out the area below this curve, but you can see that the lower sum is short of area. It means its area is smaller than the area below the function, and the area of the upper sum is greater than the area that we need. So this thing is smaller, this thing is bigger than the actual area. What we have to do, we have to make this as large as possible so that it converges to the actual area, and we have to make this as small as possible so that it converges to the actual area. So this is the idea. We have to make this as large as possible, and we have to make this as small as possible. And when this will be larger enough, this will be smaller enough, they will converge to the actual area, and finally we can say that these two things are same. How can we make this one bigger and this one smaller? How can we do that? What is the idea? One idea is, in this Riemann integral, to choose your partition in such a way. It means what we call, we have to refine our partition. It means I have to define another partition, what we call P bar, and we call this to be refinement of our actual partition P. And what is the refinement? Refinement means you have chosen first A and x1. Now you will choose some other values in between this one. Let us call this value y0, call this value y1, and this value y2, this value y3, this value y4. It means I am going to refine my partition. So P bar will be simply y0, y1 up to yn, but these all the values will be basically subset of P. subset of P, because we know exactly that y0 is same as x0 and y2 is same as x1. y2 is same as x1. Is this subset of that one, or the order is reverse? I think the order is reverse.
Refinement is in the partition.
No, refinement would be bigger. You will see. This would be bigger.
Partition one is in.
Yes, it would be bigger partition. The values would be.
Sir, your partition means over here, meaning that
same meaning. I'm taking the values. So this condition holds.
मतलब कि bounded function जी the we not operator also the union का नाम से जो बन रहा anti-list और intersection हर की निपा में
disjoint. Yes. This. So when I write this, it means the condition is bold. When I write this thing, along partition, I have this extra condition. So why am I doing this? The logic is already clear. I want to make this L to be as big as possible and make this U to be as small as possible, so that they converge to the actual area. And for this, I refine my partition. So this is what is the idea behind the Riemann integral. So let us go ahead with defining one or two other concepts, and then coming to the exact definition of Riemann integral. Should I remove this one?
Yes.
Okay, so there is a proposition that is a bit important that I want to mention. So F is bounded. We know very well it's a condition already given to us. And let's say P1 and P2 are partition of two functions of an interval. And which one is the refinement in this one? P1 contains P1 is contained in P2, or P2 contains P1. Which one is the refinement? P2 is the refinement. If P2 is the refinement, then what happens? If you take the lower sum along P1 and lower sum along P2, what is the relationship between these two? Then
P1 जो है वो subset है जी P2.
No, I'm taking the lower sum.
हाँ सर.
Which one is smaller?
उलट सी condition. Condition मतलब अगर P आता हमारे already हुई ना.
Which one is refinement?
P2.
P2. Then this will occur.
Sure.
And think why. And what about this one? I think this will happen. Do you agree why?
Yes.
Is it okay? The reason behind this is I want to make my L as big as possible. Okay. Then the value of L along P2, because P2 is refinement, should be bigger than the previous one. Because I want to make my L as big as possible. If I take P3 to be the refinement of these two, then that L would be again bigger than these two. It means I have to make my L bigger and bigger and bigger. So lower sum along P2 should be big, because I want it to be big. That's why I have done P2. Otherwise, why I have done that thing? Similarly, I want upper sum to be as small as possible. So my upper sum on P2 should be smaller than the previous one. Yes. I want to make upper sum smaller and the lower sum bigger, as big as possible. Yes. So let us put these things in a definition, what we call the definition of lower Riemann integral and the definition of upper Riemann integral. So suppose f is bounded, with f goes from closed interval to the set of real numbers, and what we do, we take the lower sum of our function to certain partition, in what we call P is partition of interval a comma b, and what I need basically, what is the idea behind this? You take the lower sum of your function corresponding to certain partition, but you want this lower sum to be as big as possible. So what you do? You change your partition. P is partition. You have to change it and you have to refine it in such a way that this lower sum becomes as much greater as possible. So I am taking the supremum of lower sums, and this supremum of lower sums is what we call the integral of f from a to b, but this integral is called lower integral, so we should give a bar there, and we call this is called lower Riemann integral. Lower Iman integral. And similarly, I am taking the upper sum of a function on some partition where P is partition of AB, and I want this as small as possible, so I am taking its infimum, and I call this to be the upper Riemann integral. Upper Riemann integral. So this is how we define the lower Riemann integral and upper Riemann integral of f. This is simply the definition. How we define lower Riemann integral and upper Riemann integral. There is a proposition that what is the relationship between lower and upper Riemann integral? This is the lower Riemann integral. Bar is downwards, the bar is upwards. What is the relationship? We want them to be equal. Okay. But if not equal, the things will look like this. Because this is lower Riemann integral, this is upper Riemann integral. But we want this to be as much greater as possible, and we want this to be as small as possible. And we want these to be same as each other. Then we call that okay, the Riemann integral of this function exists.
सर ये condition तो ये विषय लिखा है ग्रेटर जी function करो भी ये true का condition अगर function एडो भी लेला बता
always true. But it must satisfy the conditions of integrability. Otherwise, it is not satisfied. So now the final thing is what we call Riemann integral. So again the conditions are same. The function is bounded on some closed interval AB, and the lower Riemann integral is same as upper Riemann integral. This is the condition. Function is bounded, and if this happens that these two are same, then we call that this function is Riemann integrable, and what is the Riemann integral of that function is same as the lower Riemann integral, which is same as the upper Riemann integral. It means this is how you define Riemann integral. Okay, so I think the things are clear that whenever the lower Riemann integral is same as upper Riemann integral, we call that they are same, and this is exactly the Riemann integral of a function, and hence we call this f to be Riemann integrable. Can you see some changes with the ordinary notation? I have not written integral a to b f of x dx. It is not necessary, we can write. F means it is f of x, and with our definition it is clear that we are integrating along the real line, so we are not supposed to mention dx. But it is same as integral a to b f of x dx. It is same as that. That is the only difference. So this is how we define. We should keep some things in our mind, that what is lower Riemann integral, what is upper Riemann integral, what are the conditions for the Riemann integral to exist, and when these things coincide, means they are same, we call that the function is Riemann integrable, and that is the integral. These are the certain conditions that should be kept in our mind. Okay, so now we usually not use any definition to evaluate the Riemann integral, but we use the theorems. Before going to the theorem, let us discuss the Riemann integral of a function, which is very simple. The function is from 0, 1 to r, and it is defined in this way. It is equal to 1 and 0. 1 when x is a rational number, and 0 when x is not a rational number. Can we integrate this function in the sense of Riemann integral? Yes. So, what do you do to evaluate this one? What is the idea? And how we do it? We define a partition and we find the lower sum. What is the lower sum? Lower sum is this: I equals 1 to n mi n xi minus xi minus 1. It means you choose some interval. Within some interval, you have to find out the infimum. So, what is the infimum of this function? That's going to be 0. It means the lower sum is 0. And then what you do? You find the upper sum, that is defined in this way. Capital Mi xi minus xi minus 1. This is equal to 1. So this will be what? Whole sum. The lower sum is going to be 0, because if you choose any interval, the Mi is going to be 0. So this whole thing will be 0. And capital Mi is going to be 1. You can see here. So what is this sum? Xi minus xi minus 1 when I runs from 1 to n. It is called, I think, telescopic sum. You know that thing? Telescopic sum. Okay, you put here I is equal to 1, what happens?
वन में जब फिर और आखिरी टर्म
x1 minus x0. You put I is equal to 2. x2 minus x1, x3 minus x2, and so on up to xn minus xn minus 1. This is called telescopic sum. You can see, I think x1,
x0 x
all will be cancelled, only left will be this one, xn minus x0. But you know very well xn is b minus a.
0 minus.
But b is 1 minus 0, that is
One
equal
minus.
to. So this is equal to. That's the telescopic sum. Okay, so what is the lower Riemann integral? That would be equal to 0, and upper Riemann integral would be equal to 1. They are. So this function is not Riemann integrable. Basically, this is the classical example to give a counter example that why Riemann integral is not a good one. Then we should go for Lebesgue integral and so on. This is not good one. Its graph is crazy. That's a problem. That's a problem. Because when you choose any rational number, the value is 1. 0 is rational number, the value is 1. Let's say I am choosing another rational number, the value is 1. But in between this, there is another rational number, the value is 0. So for rational, the value is 1. It means this is a set of points here. So there is also a set of points here. How can you integrate this one? Because this is a function with infinite discontinuities. Infinite discontinuities. It is bounded, but it is infinite discontinuity, so you cannot find out its Riemann integral exactly. So this is how you compute it, and you will see that okay, the Riemann integral of this function does not exist. But if you find out the what we call Lebesgue integral, it exists, and the Lebesgue integral of this function is 0. Because Lebesgue integral is simply, let me tell you the bigger picture, that whatever sets are given to you, you just take the value of the function, that is 1, and multiply with the measure of that function, the set A. Let me call this set A and this set A complement. And you take 0, multiply with the measure of A complement. Measure of any rational number set is 0. And whatever this measure is, we are not interested, this will be 0. 1 times 0 is 0, plus 0 is going to be 0. So you take this value of the function that I have taken 1, and you take the measure of this set. And measure of any discrete set is always 0. In the case of Lebesgue integral. Because rational numbers are discrete and countable, we know very well. So the measure is 0. And 0 is this value, measure of this, measure of A complement we are not interested in, we are done. So we can define the Lebesgue integral, and it's going to be equal to 0. But if we reverse this idea, then it's problematic. If we reverse this idea, this is equal to 0 and this is equal to 1, then what happens? This is equal to 0 and this is equal to 1. This will be 0, we are not interested. Now the problem is, what is the measure of A complement? And what is A complement? It's the set of irrational numbers between 0 and 1. And I think it is a problem how to define the measure of the set of irrational numbers.
They are uncountable.
They are uncountable, that's a problem. If these are real numbers, then there is no any problem. If this set is whole real number, then measure of that interval is going to be the last value or the maximum value minus minimum value. The measure of interval is defined in this way. I ask you what is the measure of this interval 0 to 2. You say okay, no problem, 2 minus 0, there is going to be 2. So this is what we call the Lebesgue measure of intervals. So, but the problem is when we have rational numbers. I think that this should be same as the set of real numbers, but there is exactly the problem because you are choosing some rational numbers out of there as well. So I don't know exactly, but we'll see in this one what happens. Okay, one or two ideas, what we call the first fundamental theorem of calculus and the second fundamental theorem of calculus that we are done. We are not going for Riemann stages, but I can give you the idea what happens over there.
अच्छा सर ये जो रीमान इंटीग्रल है इनके आपने जो मींस डिफरेंट ये बताइए कि आपका फंक्शन क्लोज क्यों होता है बट उसमें जो है ना इनफाइनाइट डिस्कंटिन्यूटीज होती है तो इस वजह से
Yes, the function should be bounded and it should not be continuous, it is not necessary, but the set of discontinuities should be finite. In this one there are infinite discontinuities. It is discontinuous at each and every point. That's the problem.
With the help of Lebesgue integral, we can find. You mean that we can solve it?
We can solve it and its answer is 0. If we can solve, the answer is 0, but in the case of Riemann integral, we cannot even solve it. Because the lower Riemann integral is 0 and upper Riemann integral is 1. So what is the Riemann integral?
definition of Riemann integral.
Riemann integral means these must be same according to the definition. But these are not same, you can see.